All right. I'm at a different machine today. My son is using his own computer, so I got mine, but I'm still not in my office. There's still lots of renovation going on in our department's B building, so I think it will take a while before I can be in my office. So anyway, I have my office desktop here set up at home, so I will be from time to time I will be continuing from this. By the way, for the next 2 weeks, let's see which weeks are they. November 4 and November 11, I will have some other things that I will have to attend to. So you will have to, on November 4 and November 11, those 2 weeks, you will either have to attend the lectures the day before on Tuesday evening, or you will watch the recording that I will have for those evenings. All right, so we will skip 2 weeks of classes on Wednesday mornings. I will also make an announcement about this on OttiClass. So you will either watch the videos or attend the Tuesday evening class. We are going totally in parallel in both sections. And if you have any questions about the videos that we are going to, the chapters that we are going to talk about, you can always send an email, just like you write your questions in the chat box. All right. So this for the November 4 and November 11 lectures. After that, we are going to continue as usual. All right. So now today the plan is to talk about chapter 2 and finish chapter 2. We started talking about line segment intersection problem last week, and we have I just showed you the overview of the algorithm, and we are going to finish talking about the details of the algorithm, and we are going to learn a new data structure. Actually, this chapter is the main motivating problem of this chapter is the map overlay problem. Given two maps which define regions on the 2D plane, two separate maps, how can we find the overlay of these two maps by putting them on top of each other? And line segment intersection was something that was needed to solve the map overlay problem. So therefore, this chapter is actually composed of 3 parts. The first part is this line segment intersection, and then it talks about how we can represent a map, a 2D map, by a suitable data structure. And the second part of this chapter introduces a data structure called doubly connected edge list, or DCEL in short. I'm going to write it in the chat box. DCEL, doubly connected edge list. So we are in the second. I'm going to talk about that data structure in the second part. But the data structure is no big deal actually. It's just a table of vertices, edges, and faces. But the idea of half edges is important, I think. And although it's just a table of vertices, edges, and faces, we are going to talk about them in detail. What kind of operations this data structure supports. And the last part, which is the actual overlay algorithm, uses the same plane sweep algorithm we have used for line segment intersection. So I'm not going to ponder too much about on this map overlay part. I'm just going to talk about its main components because in terms of the algorithmic details, it doesn't have much to form the vertex and edge tables. It just uses the same line segment intersection algorithm, but to update the edges, it needs to consider different cases. So it's an efficient algorithm, but it's in terms of coding, it's still a bit tedious. So therefore, I'm not going to go into all the details of that map overlay part. But there is one portion of that algorithm which is about construction of the face records. I will talk about that part in detail. Okay, so that's the plan for today, and that will be the end of chapter 2. Next week we are going to start chapter 3. As I said, the synchronous lecture next week, we will not have it on Wednesday. Our Wednesday synchronous lecture is cancelled for next week, and November 11th too, for the next 2 weeks. You have the option, if you want, you can attend, if you're available also, Tuesday evening, you can attend the Tuesday evening lecture, or you can watch the recorded video of the Tuesday evening's lecture. All right, so if the book really describes so let's start with the line segment intersection. Let's recap the algorithm, and let's finish this first part. Then I'm going to talk about the doubly connected edge list part. And in total, all finishing chapter 2 is going to take about 2 hours today. Maybe the second hour, maybe even less than the first part. This is what happened yesterday evening. So it's not going to be, I'm not going to spend the whole 3 hours today. Okay, so the book really describes the development of the idea behind the plane sweep technique. So this line segment intersection problem really is if you read the book, especially on pages 21 and 22, it actually develops the idea really nicely. First, trying to figure out how can we avoid intersections that are unnecessary. We have talked about this. The first idea that comes into mind is to look at their y-axis projections. If there are 2 line segments, their y-axis projections do not overlap, there is no need to test for intersection because they're not going to intersect. So this gives us the idea of sweeping a line downwards and maintaining a study structure which contains the current line segments that intersect the sweep line. Therefore, if we have that set, it allows us to test intersections only for the line segments that are in the same set at the same time, which means that when we come to an endpoint, since this line segment is going to be deleted from that set, it will never be intersection tested with another line segment that comes afterwards that is going to be inserted into the set later. All right, so that was the main idea. But just having the study structure as a set, so it's also so it's really an incremental development of ideas. Okay, after we think about this, we see that in the worst case, what happens if all of the line segments are intersecting the x-axis, for example, they're all on the x-axis. Then their y-axis projections all overlap. So this will not help us to avoid unnecessary intersections. And then at that point, we see there are also unnecessary intersections for line segments that are far away horizontally too. So can we do the intersection test only for lines that are also close horizontally? Okay, and this idea helps us to improve the existing set idea into an ordered list of line segments horizontally in the study structure. So our sweep line is going downwards, and we're not just maintaining a set of line segments, but we maintain these line segments as they are ordered from left to right on this line, which will help us. Okay, we are only going to test, if this is the event point, we are going to test this line segment only with the other line segments that are close in horizontal direction as well. But this idea of closeness in horizontal is vague. How do we define it? Are we going to look for a range? In which range we are going to test for these intersections? And this leads us to the idea of, okay, why don't we just take a look at the neighbors? Okay, so that's one idea of closeness, right? This is the event point. Just test it with the left and right neighbor. So it's the idea is developed incrementally. So this way, this leads us to the lemma. If I just test the neighbors, will I guarantee? Does this idea guarantee identification of all of the intersections. Do I miss any intersections at all? And this is the lemma, actually, lemma 2.1, which is at the heart of the correctness of this algorithm. It says that if two segments intersect below the sweep line, there is some point these two segments become neighbor on the study structure. So this intersection P is never going to be missed. Okay, yeah, so there may be some noises. The cats are jumping on this trampoline, so sometimes there may be noises. Sorry about that, but now they're gone. If there is a problem in terms of the microphone, I can switch to the webcam microphone. Okay, so is my voice clear? All right. So I assume it's clear, but if there are... oh, okay. All right, thanks. Okay, so this is like an incremental development of the algorithm, which leads us to the final version of the algorithm, in which we also talk about degenerate cases. The degeneracies could be, for example, multiple line segments passing through the same intersection point. One degeneracy that we haven't considered is two segments that are partially overlapping. In that case, the number of intersection points is actually infinite. Okay, if there are two line segments which are partially overlapping, the number of intersection points is infinite. We don't want to report it as all of the intersection points, infinitely many between them. We are going to handle those cases separately. The overlapping case, that's a degenerate case that we are going to handle separately. The degeneracies that we will handle is multiple intersections at the same point, multiple line segments passing through the same point, or what if there's a horizontal line segment? How can we handle that? We can actually handle those horizontal line segments easily by considering them separately. When the event point comes to them, whatever we have on the study structure, the test could be done by just looking at the endpoints separately. Okay, so the degenerate cases, we can ignore them for now. And then the algorithm developed also, when there are horizontal line segments, how are we going to order them in the event queue? That's another thing. One thing that I stated last week incorrectly is the event queue. I told you that we can use a heap for the event queue because it supports insertion of new events, intersection events in log n time or log n time, and deletion of events in O1 time. Actually, it's also log n time, sorry. We pick the highest priority event, and removal of that is going to rearrange the heap in log n time. So all these operations could be done in log n time. But I actually overlooked the part of the algorithm that says if the intersection, or if that event, when we are trying to add an event to the event queue, it may have been discovered earlier due to some other intersection tests. For example, if there are 3 or 4 segments intersecting at the same point, and we inserted that intersection point to the event queue earlier due to the intersection test between 2 of them. But then later we do another intersection test and we identify the same event point. We don't want to add the same event point twice into the event queue. All right, so we actually also need to have a mechanism to check, does this event is this event already in the event queue? So heap is not good for this. All right, heap you can for getting the highest priority element, for inserting, for deleting, for inserting a new element. Heaps are good. They do that in log n time. But if you want to say search for something, heaps are not good for searching. If you want to say search, for example, does this point exist in the event queue? actually for heap you will have to record, it will require on time, not log n time, because if you remember heaps, the highest priority one is at the root node, but the left and right subtrees are just distributed arbitrarily. The left and right subtree, unlike binary search tree, the left and right subtrees do not help us to search for a particular node. All right, so that's why heaps are not good for. If you're going to check the existence of an event in your event queue, you shouldn't use a heap, but instead use a balanced binary search tree, which will also help you to remove. I mean, you can, in log n time, you will be able to remove the smallest node in your balanced binary search tree. You will be able to insert some event in log n time. You will also be able to search in log n time as well. Okay, so for event points, we also use a balanced binary search tree, just like we do for the status structure. So this was the algorithm, the find intersections. The actual algorithm pseudocode was the handle event point. This main function is just saying that get the next event, handle that event, and nothing else. All right. So here the actual thing is going on in this handle event point function, and this is a nice running example that tells us how this handle event point function runs. So if you remember, we defined three sets at this associated with this three possible different sets that are associated with this event point P. So this is our event point P. Let's call the line segments whose lower endpoints are associated with this event point P. Let's call this set L. That's the set L. All the line segments whose upper endpoints are associated with this event point P they comprise the set U. Okay, so U is, for example, right now in set U there is only S2. S2 is in set 2. S4 and S5 are in set L in this example, and there is the third set which contains S1 and S3. These are the line segments which contain this event point P in their interior. Okay, that's the set C. So these three sets are the main three type of line segments that can be associated with this event point. First of all, it's clear that set L has to be deleted from the status structure, which is S4 and S5. As the sweep line moves downwards, they will no longer be in the status structure because those line segments, we stop intersecting those line segments. All right, so S4 and S5 has to be deleted. So we delete S4 and S5, set L is deleted. And then S1 and S2 is going to be inserted. So that's clear because that's this set U. All the segments in set U, they have to be inserted into the status structure. What about S1 and S3? Sets C, what we do is we first remove them and then we reinsert them. Because if you look at this balanced binary search tree, even at the intermediate nodes, we have the segments. These are not scalar values that you can compare. For example, I have S1 here. If you're searching for S4, is S4 to the left of S1 or to the right of S1? So when you have line segments, this, whether a segment is to the left or to the right, is not something you can tell globally. For example, look at S1 and S3. If I ask you, is S1 to the left of S3 or to the right of S3? Okay, since they both have two endpoints, this may not be globally true. You can only answer this question with respect to a pivot point, for example, or with respect to a sweep line. You can say, for example, if I ask you the question like this, if above the sweep line L, is S1 to the left of S3? And the answer would be yes. And while below sweep line L, is S1 to the left of S3? No, it's to the right of S3 below the sweep line at this point. So with respect to this pivot point, or with respect to this horizontal line, S1 and S3's order are going to change. Therefore, when we have this, when we implement this in C++ using the standard template library, for example, when we're using a set or a map, or an ordered map, what we will need is a comparator function, which will it will be the comparison operator. That's what we need. I mean, in order to compare two line segments, we need to write our own comparator function, and this comparator function for the case of line segments should also get as input the pivot point, the event point, or the sweep line's y coordinates. So above this y, below this y, the order may be different. So implementation wise, you need to consider these tricky points because you have line segments and you have to have a function to compare two line segments which will return less than, greater than, or equal to type of results. Okay, so while we're doing this, okay, we remove set C here, the segments S1 and S3 is removed and added. So this sweep line, actually at the exact point of this sweep line, at this event point, S1 and S3, or actually all of these line segments, they're all equal, right? They all pass through the same point. So in terms of their ordering, this point is like a singularity. At this point, we cannot order them from left to right. So therefore, again, while implementing, given this pivot line, sweep line that we are going to compare them against, we have to do the comparison slightly below this line. Epsilon below this line, the singularity dissolves. There is no singularity below this line, and we have the ordering nicely from S3, S2, S1. This is how they should appear on the balanced binary search tree. Therefore, we need to also be careful in not using the pivot exactly the same line, but epsilon below sweep line is actually how we should insert them. We should order them on the balanced binary search tree. It may also be very difficult to implement, but how are you going to decide on this epsilon? It shouldn't be too small because it should be larger than the floating point precision. So I need to be able to really compare them left and right. Yeah, we are always going to apply epsilon, but deciding on the amount of epsilon is difficult because every time we are inserting into the sweep line, we should always insert them, whatever the pivot is, we should always use epsilon, we should always use a line that is slightly below that pivot line. Okay, so we are always applying epsilon, but here the problem is, what should that epsilon be? If it shouldn't be too large, so that we shouldn't pass over the next event point. When the points are too close to each other, it should be actually smaller than the distance of the closest points. Yeah, we can also increase precision. You can always use double precision for this computation. Slightly before, you mean above the sweep line? If we apply epsilon slightly before, if we don't want to order them so that we are not interested in what happens above the sweep line, because we are inserting them such that the status structure, how the status structure is going to look after this event point and before the next event point. Okay, so between this event point and the next event point, which may be this, for example, this status structure should reflect the situation between this event point and this event point. Therefore, the epsilon should be in such a way that what will happen slightly below the sweep line. All right, so that's theoretically, it's easy to describe, but when it comes to implementing this, actually, when I tried to implement this line segment intersection myself, that was one of the parts that was tricky for me to implement, how to decide on that epsilon. Okay, so especially, I mean, this is okay when you have this few number of line segments in which the event points are far away from each other. Epsilon could be 0.1. That's okay. Okay, 0.1 would be a good epsilon here if the smallest distance between any 2 points is more than 1. Okay, but if you have thousands of line segments, it may be the case that the points are really close to each other. So you need to choose an epsilon smaller than that, but larger than your precision. Yeah. Yeah, it might work. Yeah, what you're suggesting is, so any ideas in terms of implementation, taking the minimum floating point, converting to a double will work for an epsilon. That's a really good idea. Yeah. So you can choose your epsilon as the smallest floating point number. I think that will be okay. And if you decide also, I mean, if 2 points or 2 endpoints are really close, and if you treat them as equal points, that's also another thing. I mean, if you have really close points, you cannot avoid, at some point, you have to treat them equally. You need to treat them, these points are actually the same points. Your epsilon could be slightly larger than what you're suggesting that these are equal, okay? Yeah, those are all really good points. So, therefore, deleting C, the set C, and reinserting them reorders them, okay? So the algorithm was like this. If at any point, I mean, if you look at step 3 of the algorithm, if these 3 sets, the union of them, the union contains more than one segment, it means that there's an intersection at this point, and we need to report this intersection. Otherwise, if there's only one segment associated with this event point, that's not an intersection. So, and the last thing is, okay, after we do this, which intersections are we going to test now? The new intersection test we need to perform. Potential intersections, the neighborhood changes. For example, what I can see here is that now S3 became neighbors with S7. So whatever the set we have below the sweep line, this set, now I'm going to look at this, the union of set U and C, because L is gone. There is no, the set L, the segments whose lower point were associated with P, they are gone at this point. They can never contribute to intersections below the sweep line because they do not exist below the sweep line anymore. So therefore, I'm just interested in, let me zoom in. So I'm just interested in set U and C here. If the so what does this line 8 says? If there are no such line segments, if set U and set C, if they were empty, what it means is that this event point P was only associated with line segments which ended at this point. So if there is nothing here below this point, should I do anything? Should I test for any intersection? I mean, imagine S3, S2, and S1 are gone. They do not exist. Only S4 and S5 were here at this event point. Imagine S1, S3, S2 doesn't exist in this example. There is only S4 and S5, and they're deleted. When we delete S4 and S5, do I need to test any intersection below this event point P? I mean, if you look at the function, it says, yeah, you have to test some intersection because there's that if condition. But which ones am I going to test intersection with? And it says right here, it's actually S7 and S8. All right, S7 and S8 became neighbors due to this event point, due to the deletion of S4 and S5. They were not neighbors before S4 and S5 were in the status structure, but after they're deleted, S7 and S8 become neighbors if S1, S2, S3 doesn't exist. All right, so therefore step 9 and 10 actually tells us that find the left and right, immediate left and right neighbors of this event point in the stutter structure. And we can find this because this is a balanced binary search tree. We can perform this query and say that, okay, let's find these two segments to the left of this event point P. After we find them, we test for it. So this find new event function, I'm going to come to that soon. And it's testing intersection between these two segments. So this is the function where we test for intersection. If there's an intersection below the event point, we will add to the event queue. All right, if it's not empty, if there are some line segments in this union, the new line segments, the existing line segments that are passing through this event point, what we do is, it's this case, if S1, S2, S3 exists, which intersections we should test this time. For example, if there are 7 line segments here that are associated with this event point here, do we need to test all pairwise intersections in between these 7 of them? The answer is no, because all the ones that are in U and C, all the segments that are in U and C, they're already reported as intersecting at this event point. Okay? 2 line segments cannot intersect at more than 1 point. I mean, if they're overlapping, that's another issue, but let's ignore overlap in line segments. If you have line segments that are intersecting, since these are lines, they can only intersect at 1 point. I mean, if they intersect at here, can they also intersect below the sweep line? No. So there is no need to check for intersection for this between the line segments that are in U and C. However, look at S3 versus S7 and S1 versus S8. These are the 2 intersection tests we need to check. The leftmost element of this U union C set is S3. That's the leftmost member. We find its immediate left neighbor and we test intersection with that. The rightmost element of this U union C set is S1. We find this immediate right neighbor and we tested intersection with that. So these are the 2 find new event calls that actually describe that in pseudocode. So let's S prime be the leftmost segment of this union, find SL, the immediate left neighbor of S prime, and test intersection with those. S double prime, the rightmost segment, SR, the immediate right neighbor, test intersection with S double prime and SR. And that's it. The find new event is just 2 lines of code with just a single if statement saying that if there's intersection, okay, so we test intersection in this if statement, and if the intersection is below the sweep line, this is important because if it's above the sweep line, it must mean that we have already discovered and reported it. We are only interested in new intersections that are potentially new event points. By the way, that intersection is not reported at this point. That's another important subtle thing that you should note. When SL and SR intersect below the sweep line, this is not the time that we reported as an intersection. We just insert that point as an event queue, as an event point to the event to the queue. When its time comes, when we come to that event, that's the place where we report that intersection. Okay. If the intersection is not, this is another part of the event, this if statement. If the intersection is not already in the event queue as an event point, if it was already inserted due to some other line segments, we shouldn't add it again. All right. So one thing so I will also give your first written assignment. And one of the questions in that written assignment maybe I plan to give, for example, give an example setting of line segments in which the same intersection at that point is detected twice. Okay, it was detected before, inserted into the event queue, and we come at this point and the intersection actually is present as an event in the queue. Okay, so it's not very difficult to come up with an example to show that same intersection is detected twice as you move along plane, with the sweep line. Okay, and that's it. We insert it into the event queue. So this concludes the line segment intersection part of this chapter, the first part. And I just want to mention these last two lemmas in this first section. The correctness and time complexity of the algorithm is proven in two different parts. In different chapters, you're going to see that we can have a single theorem that states that, okay, this is both correct, and it solves it in n log n time, or it also states something about the computational or space complexity. And here, in this second chapter, the correctness and time complexity is separated into two parts. The first part is only about correctness. The correctness proof actually relies heavily on the previous lemma that was proven, in which when two line segments intersect, they have to become neighbors on the study structure at some point above the sweep line. So the lemma 2.1 is actually really critical to the correctness proof. The second part is about the time complexity proof. And there's something interesting. There are two things that are written here. Okay, again, a very subtle difference. Look at these two statements, m plus k log n and m plus I log n. First of all, what is k and what is I? Let's see. K is the size of the output, and I is the number of intersections. Isn't k and I the same? The answer is no. If multiple line segments intersect at the same point, the output is going to contain all those line segments, but in terms of intersection, that point is considered as one intersection. Okay? If there are 7 line segments intersecting at that point, the output size may be 7 line segments, but that intersection is counted once. Okay? So this I is some smaller number than k. Okay, k is at least I. Okay, so this is a more strong result that it's the computational complexity actually. The running time is this. If we just report that there's an intersection at that point. Okay, if you're going to actually report all of those intersections that are here. I mean, this k could be on the order of n squared if there are n squared intersections, but there's something really interesting. It says that even number of intersections is n squared, the number of things that you report, the output size, cannot be too large due to the fact that if you report some line segment as intersecting in one part of the output, you cannot report the same line segment again in other part of the output. So the output also is like limited. This k is limited in terms of n, the number of line segments. I mean, you could also, that's another way to prove it, but this part of the proof is actually relies on Euler's formula about planar graphs, saying that if we have, this is our intersection, so this is the figure that it uses. If there are intersections, the number of vertices, the number of edges and faces on this planar graph are limited. They are related to each other with some kind of a linear formula. This was the Euler's formula. So this is really nice. This is the relation. Let me show you. The Euler's formula states that if we have a planar graph, the number of vertices minus number of edges plus number of faces is actually, this should be equal to 2, greater than or equal to 2, as stated. Equality holds if and only if the graph is connected. If we have a connected graph where all the vertices and edges are connected, for example, for meshes, for triangular meshes, this equality holds if it's a connected mesh. But so this is the equality that it uses. By using this, it says that it cannot be, I cannot be that large, okay, than the number of intersections. So, but I'm going to skip this part. This is really not that important. The important part is if the number of intersections is on the order of n, if we don't have too many intersections, we have an ourselves an n log n algorithm. But the another point is this is an output sensitive algorithm. If there are too many intersections larger than order of n, we will have to spend more time. So just consider that this is an output sensitive algorithm, but if the intersection is on the order of n, we have ourselves an efficient algorithm. Okay, so this concludes the first part. I just skipped over the correctness and time complexity proofs, but if you understand the basic idea of plane sweep, the main components, the sweep line, the status structure, which is really important, and the event queue, in which we had a dynamic event queue, that should be sufficient for this chapter's purpose. All right. Now, in the last 10 minutes before the break, I'm going to introduce you the doubly connected edgeless data structure, in which we are going to use it to solve the map overlay problem. So let's come to the second part of this, the doubly connected edge list. So the doubly connected edge list is just 3 tables in terms of data structures. As data structures go, it's not very elaborate, or it's not it's not very difficult data structure in terms of implementing. It's just 3 tables. So any subdivision of the plane, so any map like this, could be represented as something like this, okay, in which we have vertices which are potentially connected by edges, and which form connected maximal subsets on the plane, which we call faces. Okay, so here is how a face is defined. A face of a subdivision of the plane is a maximal connected subset of the plane that doesn't contain a point on an edge or a vertex. Okay, so it's like the area which we don't have anything other than the empty area. Okay, so it has edges and it has vertices bounding it. So this will be a face. Okay, actually, let me undo this. And what I'm going to do is I'm going to show, this is what I did yesterday. I copied this one to GIMP to show some different faces and interesting things. There are also polygons which are not simple here. A face here is not necessarily a simple polygon. It may be concave, convex, and actually you're going to see a face may have, let me enlarge it a little bit, holes in it. A face may have holes in it, and as we see in this example. So let me move it over here. All right, now let me also flatten it. Yeah. Here, look at this face. Actually, I wanted to select this pattern fill. Nice pine wood tiling here. So look at this face, okay? If this face is not a simple polygon, it has an outer boundary, and there's a hole inside this face as well, which is not part of the face. When I say this is the maximal connected subset, here is this donut-like shape. That's the face. Okay, it doesn't include anything that is here. This the inner part. This is another face, which is also like it also contains a hole in it, and this is yet another shape that is inside. Okay, so I have three faces here. These are all faces, and there's also an unbounded face, which is at the outside. I think it's not a good. Yeah, so this is the unbounded face. That's also a face. This is a subset of the subdivision, which is not necessarily bounded. So it doesn't have an outer boundary, but there are holes in it too. Okay, so these other faces, this part, for example, appears as a hole inside the unbounded face. So how many faces I have here? 1, 2, 3, 4, 5. Actually, I can use 3 here. 4, 5, 6, 7, 8, 9, 10, 11, and 12. So there are 12 maximally connected subsets of the plane here, which we can identify as faces. So each of those faces, except this unbounded one, has a unique single outer boundary. Okay, every face has one outer boundary, and it may potentially have multiple holes in it. A face may contain multiple holes in it. And the way we are going to represent the edges that bound these faces is that's actually the interesting part in doubly connected edge list. We are going to have these edges represented as two half edges because we want them to be directed. So here's how a face is going to look like. Let me zoom out. Yeah, let's look at this one. Yeah, this figure is better. Yeah, if you look at this, the directed edges that we see here, they actually have a twin. Each directed edge will have the twins are not shown here. This is shown as an undirected one, but the twin edge will be an ordered edge in the opposite direction of this one. Okay, this one has a twin in the opposite direction, and this one also. Every one of those edges will be represented as two half edges. And what will happen is that we will an edge will be incident to a face. I mean, the edge will be bounding the face that is always to the left of it. For example, this edge will belong to this face. It's bounding this face to the left of it. Again, this edge, its face is also this one. Okay, so both edges, this one and this one, is bounding this face here. So the face related to an edge, associated with an edge, will always be to the left of it. All right. And what about this face here then? The edge actually that bounds this face will be the twin of this one. If you draw the twin from this vertex to this vertex, you'll see that it's bounding this face will lie on its left. All right. So this half edge idea is actually, again, a very critical component of this doubly connected edge list. For vertices, let's actually take a look at quickly an example doubly connected edge list. So this is the running toy example I'm going to describe, and we're going to detail and give more details probably after the break. But if you look at this, for a we have three tables. A doubly connected edge list is nothing but three tables: a vertex table, a half edge table, and face table. Okay, so since there are two faces here, I have F1 and F2. It contains only two rows, and there are four vertices here. For the vertices, I only need its coordinates. It's a two-dimensional map, so we will have two-dimensional vertex coordinates, and an incident edge, which is one of the edges arbitrarily, in which this V1 is an origin of. So each edge actually contains two vertices. Since it's ordered, there is an origin and destination. For example, this E41. E41's origin is V3 and its destination is V2. And when we are storing this information on the table, we don't store the destination because for half edges, what we are going to actually report is that each of those half edges, they will form a chain. I mean, the chain, whether it's an outer boundary or it's the boundary of a hole, they will form a chain. So we are going to be using the next pointers. The next edge will be uniquely defined. For every edge, a unique next edge is defined. That means they are bounding the same face, and it's the next edge on the outer boundary. Okay, and whether it's the outer boundary or inner boundary, this will be, we will come to that later. Actually, before the break, let me ask you this question. Look at these two boundaries. This is the outer boundary. This is the boundary, again belonging the same face, which we call the boundary of a hole. Okay, do you notice a difference between these two boundaries? You can write the answer in the chat box. I mean, look at these edge chains. What is the main difference between these two edge chains? Any ideas? Exactly. One of them is counterclockwise, the other is clockwise. And this is always the case. The counterclockwise edge chains will always be an outer boundary of a face. And the clockwise chains will be one of many, potentially many, inner boundaries or boundaries of holes in a face. So in the face record that I show here, the inner components may actually be a list of edges. That's one edge from the inner boundary will be sufficient, because by following the next pointers, I will be following the entire boundary of the hole. But since there may be multiple holes in a face, so this may be a list of inner components. So inner components is potentially maybe more than one, but the outer component is always unique for every face, and it will be null or nil only for the face that is unbounded. The unbounded face will not have an outer boundary because it's unbounded, but all the other faces in our subdivision will have a unique outer boundary. Now, if I give you an edge table like this, can you identify how many outer boundaries are there? What we need to do is start with an arbitrary edge. By following its next pointers, we form ourselves a chain. So it's like depth first search or breadth first search, whatever you call. So because I mean there are actually many disconnected components here. You start with an edge. By following its next pointers, when you come to that same edge again, what you have here is an edge chain. Now, the question is this chain an outer component or an inner component? Sorry, I meant to hit this one. Let's come to this and let's get ourselves a new figure. Yeah. Now, if I give you an edge chain, by looking at it, actually, you will be able to see whether it's clockwise or counterclockwise, right? I mean, by looking at it, if I tell you something, if I give you a chain of edges, you will be able to see by just looking at its shape, you are going to understand it's clockwise or counterclockwise, right? So here is a question for you. Is this, by just looking at these two edges, is this counterclockwise or clockwise? Any answer? Any ideas? So this is actually a trick question. So it looks like it's counterclockwise, right? Or can it be clockwise? Of course, right? I mean, if you do it like this, you see what happened. I made it a clockwise chain. But it could also be counterclockwise. Okay, now given an edge chain, can you determine whether it's clockwise or counterclockwise? Because by using that, you need to determine whether it's an outer boundary of some face or if it's the inner boundary of a hole. So given an edge chain like this, we need to be able to determine that. And the rule in the book is this: you look at the leftmost vertex of a chain and identify the two edges, the previous one and the next one, that are associated with that vertex. I mean, in which the previous one is in which this vertex is the destination, and the next one is in which this vertex is the origin. Okay, so let's look at these two edges. If the angle from previous to next is less than 180 degrees, that must be a counterclockwise cycle. Otherwise, it has to be, let's do the same thing, okay? And I want to do something clockwise. Okay, so this is a clockwise orientation. And if you look at, again, the leftmost vertex, by the way, this rule holds only for the leftmost vertex. If you look at the leftmost vertex, this time this is going to be previous, this is going to be the next. And if you look at the angle from previous to next, following again the left hand side. We actually, since we know that always the left hand side of is the face, all right, so therefore we need to draw this angle so that it's the angle is on the left hand side of both of those edges. So here the left hand side angle is this one. As you can see, it's greater than 180 degrees. If it's greater than 180 degrees, it's clockwise. Otherwise, it's counterclockwise. So this is the rule that we will be using to determine whether an edge chain is outer boundary or inner boundary. And given an edge list like this, if we identify all the outer boundary chains, their number plus 1 will give us the number of faces. Okay, so that's how we are going to use the outer boundaries. All right, so let's have a 10-minute break now. Let's meet at 10:45. All right, and after that, after we meet, I'm going to finish this doubly connected edge list and briefly describe the method we are going to use for the map overlay problem. All right, so let's. I'm stopping sharing now and the recording. We will meet at 10:45.